It's still dark when you step outside, but the sky doesn't look like night. A pale glow hangs above the horizon, faint but unmistakable. Not sunrise, not fire, not weather. You pause, trying to understand what you're seeing. Thin bands of light stretch across the sky, red in places, whitish in others, slowly shifting as if the atmosphere itself is moving. People begin to gather in the street. Some point upward, some argue. A few insist the sun must be rising early, but the clocks say otherwise. This is not happening on Earth. In late August and early September of 1859, the sun releases an enormous burst of energy. It travels across space and strikes the planet without warning. There are no satellites to detect it, no instruments to forecast it, no one looking for danger. And as the sky glows in impossible colors, something else begins to react. The world's newest system of wires, the one carrying information faster than humans ever have, is about to be driven by a force no one has planned for. In 1859, the world is not electric. There are no power grids, no radios, no satellites moving silently overhead. Most homes still rely on candles and oil lamps. Factories run on steam. Messages travel at the speed of horses, ships, and trains. But one technology is quietly changing everything: the telegraph. By the late 1850s, thousands of kilometers of iron and copper wire stretch across North America and Europe. They follow railway lines, they cross rivers and plains, they connect cities that once felt impossibly far apart. For the first time in human history, information moves faster than people. A message sent from New York can reach Chicago in minutes. News from Europe arrives days earlier than it ever has before. Financial prices, military updates, railway schedules, all of it now depends on electrical signals clicking through wires. Entire economies begin to synchronize around this network. Inside a telegraph office, the system feels dependable. You might be standing beside a wooden desk, watching a strip of paper tape slide steadily through the machine. The room smells faintly of oil and warm metal. Each click represents a message crossing hundreds of kilometers. Click, click, click. This technology feels modern, efficient, controlled. But it has one vulnerability no one has considered. These wires are long, they are exposed, and they are grounded directly into the earth. They were designed to carry small, controlled currents generated by batteries. They were never designed to interact with forces beyond the planet. No one has tested this system against the sun, and no one realizes that, at this very moment, the Earth itself is about to become part of the circuit. On the morning of September 1st, 1859, something happens 93 million miles away. The sun releases a massive burst of energy. Not slowly, not gradually, but all at once. In England, an astronomer named Richard Carrington is carrying out a routine observation. Carrington is not studying disasters. He is mapping sunspots, dark regions on the sun's surface, part of an effort to understand solar behavior. He projects the image of the sun onto a screen, as astronomers commonly do. Then, without warning, something extraordinary appears. Two intensely bright points of white light erupt from a sunspot group. They are not reflections. They are not artifacts of the equipment. Carrington initially believes something has gone wrong with his eyes. Then he suspects the telescope. The brightness is overwhelming. The entire event lasts only a few minutes. Carrington carefully records the exact time and position of the flare. Then, just as suddenly as it appeared, the sun returns to normal. What Carrington has witnessed is now known as a white light solar flare, a rare type of eruption powerful enough to be seen in visible light. At the time, no one understands what this means. But that flash has released enormous quantities of energy, including charged particles capable of traveling through space. Most solar activity never reaches Earth in a meaningful way. The planet's magnetic field usually absorbs or deflects it. But this eruption is unusually strong, and Earth's magnetic environment at that moment is unusually vulnerable. Within hours, the energy released by that flare reaches the planet. It strikes Earth's magnetic field directly, compressing it and forcing electrical currents into places they do not normally flow. No one on the ground knows this. There are no satellites monitoring the sun, no instruments measuring space weather, no warning systems of any kind. Carrington has recorded the cause, but the effects are already moving through the Earth, and they are about to reveal themselves, first in the wires and then in the sky. The first signs appear quietly. Inside telegraph offices, operators notice that the equipment is behaving strangely. Sounders begin clicking when no one is touching the key. Messages arrive incomplete. Lines go dead, then suddenly return. At first, it feels like routine failure. Telegraph systems are mechanical. Wires corrode. Batteries weaken. Connections loosen. Operators adjust contacts and check their power supplies, expecting the problem to pass. Instead, it escalates. Some operators report electrical shocks when they touch the keys, strong enough to startle, strong enough to force them to step back. In several offices, sparks leap from metal components. Paper tape ignites. Insulation begins to smolder. These are not isolated incidents. Reports emerge from telegraph stations across North America and Europe, describing similar effects at roughly the same time. The system is failing everywhere. In an attempt to protect equipment, some operators disconnect their batteries entirely. They expect the machines to go silent. They don't. Messages continue to transmit. With no power source attached, signals still travel across the wires. Operators watch in disbelief as electrical current flows through a system that should be inert. The only possible source is the Earth itself. The storm has disturbed the planet's magnetic field so violently that it is inducing electrical currents directly into long stretches of wire. Telegraph lines, designed to carry small, controlled currents, now behave like massive antennas. They collect energy from the environment and feed it straight into the network. For the first time, a human communication system is being powered by a force from space. No one understands this yet. There is no concept of solar storms, no understanding of geomagnetic induction. All operators know is that the system they depend on, the system that synchronizes news, finance, and transportation, has become unstable. Messages can no longer be trusted. Timing collapses. Control evaporates. And as telegraph offices struggle to contain the damage, something else becomes impossible to ignore. The disturbance is not confined to wires. Outside, the night sky begins to change. As telegraph systems struggle, the effects of the storm spread beyond the wires. Night falls, and instead of darkness, the sky begins to glow. At first, it looks like distant firelight low on the horizon. A deep red haze that shouldn't be there. People step outside. They stop what they're doing. They look up. Across North America and across Europe, similar reports begin to surface. The sky glows red, In some places, white. In others, pale green. The light stretches upward in broad bands and curtains, slowly shifting as if the atmosphere itself is moving. In several towns, the glow is bright enough to see the ground clearly, bright enough to read by, bright enough that people believe the sun is rising early. Newspapers later describe citizens waking their neighbors, convinced that a distant city must be burning beyond the hills. Farmers begin their morning routines in the middle of the night. Lanterns are brought outside, then lowered because they are no longer needed. At sea, sailors report luminous skies spanning the horizon. Some navigators notice that compasses hesitate, drift, then settle in slightly wrong positions. Not everywhere, not constantly. Just enough to make experienced crews uneasy. No one understands the connection. There is no broadcast explaining what is happening, no authority issuing warnings or reassurance. Each community invents its own explanation. Some believe the event is atmospheric. Others believe it is astronomical. A few believe it is a sign. What they are seeing is physical. High above the Earth, charged particles from the sun are colliding with gases in the upper atmosphere. Those collisions release energy as light. Normally, Earth's magnetic field confines this effect near the poles. But during this storm, the magnetic field is severely disturbed. The auroral zone expands far beyond its usual boundaries. That is why the phenomenon appears in places that almost never see it. And that is why it feels unnatural. Because people are watching the invisible shield around their planet deform. Inside telegraph offices, wires continue to behave unpredictably. Outside, the sky behaves like a warning signal. For the first time, a connected civilization experiences something new. A global event that does not respect borders. A force that touches cities, oceans, and wires at the same time. No one can see the eruption on the sun from here. No one has language for space weather. All you can do is stand under that red sky and realize one thing. Whatever this is, it isn't finished yet.
This message confirms the delays.
As the storm continues, its effects spread through the systems people depend on. Not dramatically, but quietly. The telegraph network no longer behaves as a single system. Messages arrive late. Others arrive out of sequence. Some never arrive at all. Railway operators begin to notice the consequences first. Train schedules rely on telegraph timing to prevent collisions. When messages fail or arrive incorrectly, trains are delayed or stopped entirely. In some regions, rail traffic slows to a crawl. News transmission falters. Newspapers wait longer for reports. Market prices arrive too late to be useful. Information that once moved in minutes now takes hours, or doesn't move at all. Financial coordination weakens. Merchants hesitate to commit to prices they cannot verify. Orders are delayed. Transactions stall. None of this looks like disaster from the outside. There are no explosions, no crowds in the streets, no visible collapse. But the rhythm of daily life begins to drift. The telegraph had quietly synchronized distant places. Now that synchronization is breaking down. Local decisions replace centralized ones. Operators rely on judgment instead of confirmation. Rail managers choose caution over speed. Editors publish partial information, unsure what can be trusted. The storm exposes something new. This technology was not just a convenience, it was a dependency. For the first time, societies experience what it feels like when a connected system fails without warning. And yet, the disruption remains limited. The storm does not last forever. As the sun's activity begins to subside, currents in the wires weaken. Equipment slowly returns to predictable behavior. By the end of the event, most systems resume operation. Life continues. But something has changed. A boundary has been crossed. Human infrastructure has been affected directly by a force beyond Earth. The lesson is subtle and easy to miss. The world did not end, but it was briefly reminded that its newest nervous system is vulnerable to forces no one controls. The event of 1859 was not an ordinary solar disturbance. The sun produces flares and eruptions all the time. Most of them never affect Earth in any noticeable way. What made this storm different was a rare combination of factors. First, the eruption itself was unusually powerful. The flare observed by Richard Carrington released an enormous amount of energy in a very short time. It was strong enough to be visible in ordinary light, something that almost never happens. Second, the eruption was directed toward Earth. Much of the sun's activity travels harmlessly into space. This one did not. The charged particles were launched on a path that intersected directly with Earth's orbit. Third, the timing was dangerous. Earth's magnetic field is not constant. It changes in strength and shape depending on conditions in space. At the moment this storm arrived, the magnetic field was already disturbed. That made it easier for solar energy to penetrate and deform it. Together, these factors produced an unusually intense geomagnetic storm. The planet's magnetic shield was compressed and shaken, forcing electrical currents into the ground, the oceans, and any long conductor connected to them. That is why telegraph wires reacted so violently. They were not overloaded by human power. They were energized by the planet itself. Scientists today classify the Carrington Event as the most intense geomagnetic storm ever documented. Not because it caused the most damage, but because of how strongly it disturbed Earth's magnetic field. And this matters for one reason. The storm did not target technology. Technology happened to be in the way. The sun did not change its behavior because humans had built wires. Humans had simply built systems that could interact with solar energy for the first time. That interaction was accidental, and it was a preview. If an event like this happened today, the sky would not be the first thing to react. Satellites would. Modern society depends on thousands of satellites orbiting Earth for communication, navigation, weather forecasting, and timing. A powerful geomagnetic storm would disturb those orbits. Sensors could be damaged, signals could degrade or fail. Navigation systems would feel it next. GPS relies on precise timing signals from space. Even small disruptions can introduce errors measured in meters or more. Air traffic, shipping, and emergency services depend on that accuracy. On the ground, power systems would face a different kind of stress. Modern electrical grids use long transmission lines, much like the telegraph wires of 1859. Those lines can collect geomagnetically induced currents during severe storms. Transformers are especially vulnerable. They are large, expensive, and difficult to replace quickly. This does not mean instant collapse. Most storms cause little or no damage. Grid operators monitor space weather and can take protective measures. But the risk exists. Unlike 1859, today's world is synchronized in real time. Finance, logistics, healthcare, and communication all rely on uninterrupted electrical coordination. A disturbance does not need to destroy infrastructure to cause disruption. It only needs to desynchronize it. The lesson of the Carrington event is not that catastrophe is inevitable. It is that exposure has increased. In 1859, the storm revealed a vulnerability humanity barely noticed. Today, the same interaction would be felt everywhere at once. Not because the sun is more dangerous, but because the world is more connected. When the storm finally fades, life resumes. Telegraph systems stabilize. The sky returns to darkness. The unusual becomes a memory. There are no monuments built to mark the event, no official inquiries, no global response. In 1859, the world is still simple enough to absorb the shock. The wires recover, the sun quiets down, and humanity moves on. But something important has happened. For the first time, a force from beyond Earth has directly interacted with human infrastructure. Not symbolically, but physically. The planet's magnetic shield bent. Electrical systems responded, and society briefly lost synchronization. The Carrington Event becomes a historical footnote, not because it was insignificant, but because the world was not yet dependent enough to feel its full consequences. The warning arrived early, long before the systems that would make it dangerous were built. And that is the quiet lesson of 1859. The sun does not need to change. Only the world beneath it does.